Okay, so we're going to take a break from kinematics and do something different. And the reason why is because we haven't actually done any physics yet. And so I wanted to do some physics where things are going to work out rather simply, because when we get into the next stage of kinematics, which is Newton's laws, or the laws of motion, it's a little more complicated. And so I want to use a simple principle to illustrate this, and we're going to use something called geometric optics. Okay? The geometrical optics is a branch of optics that is accurate for light within a certain region, as long as because we'll learn later that light has a wave-like nature, right? And if the objects that we're interested in interacting with it are on the order of the wavelength, then we have to talk about the wave nature of light. Okay? If they're not, though, if the objects are much larger, then we can talk about things in terms of ray optics. And so we can treat light as a ray, which is something that has a direction. Okay? So they're just lines going in a direction. Okay? And so one of the first observations on light was the idea of reflection. And so this was originally done by Heron of Alexandria, probably around the 1st century AD. And he considered, why is it that light reflects the way that it does? And so if we consider a flat mirror, and we were to, take a laser pointer, which Heron of Alexandria wouldn't have had at the time, and bounce a ray off of it, we would see that it comes in, hits some point, and will reflect out here somewhere. You can kind of see it there. And so Heron was curious why that would be, if he could understand that. And so the first attempt at understanding light was an idea called the principle of least distance. And so if we consider that this black line here is our flat mirror surface, and we consider 2 points, A and B. And we're going to say that the light begins at point A and it ends at point B. So we have an observer here at B, and we have someone emitting light at point A. Let's consider all the possible paths that it could take. Now we know it bounces off of this mirrored surface somehow. But what's the path? How do we figure out what the path is? So here I've drawn a few different paths. The brown path, which just comes straight down, hits the mirror, and then bounces over to B. And I've measured, using a ruler, what those path lengths are. And so for the first arm, going from A to the mirror, I have a length of 25 centimeters. And from this point up to B, I have a length of 40.5 centimeters. And so I'm just going to add those two numbers up. I get 65.5. Now we'll consider the black line that I've drawn here. And if I measure the path lengths here, I get that it's 29.5 centimeters for the first leg and 29.5 centimeters for the second leg. So I kind of split the difference between the two. When we add that up, we get 59 centimeters. And then I'll consider another ray, which goes from A to this point here on the mirror, and then back up to B, and those path lengths are 35.5 and 26.5, which add to 62 centimeters. And so if we look at these three different possible light paths and notice something about the black path, that it has the minimum value, that's the minimum distance. And so this is kind of the origin of the principle of least distance. And so Heron thought about it, well, how can we tackle this from a theoretical point of view and make sure that what we're doing is absolutely right? So we need a good principle here. And one principle that you're probably familiar with already is the idea that the shortest distance between 2 points is a straight line. And so what Heron saw, right, was a straight line being the path forward on this. And so let me just observe that the distance from B to this line, the mirror, is 25 centimeters. So if I extend that line out in the other direction, let me go from 25 to 25 below the mirror's surface, which is going to put us down right about here, somewhere there maybe. And now I'm going to connect up this point A with this point that I've drawn down here. Hopefully I've been careful enough. And what we will see is that the distance between these 2 points is the same. So I'll call this H, and this is H. So you can imagine that if I were to take this mirror and fold it over, right, that this line would come right back on top of this black line. And so this virtual point here, as we'll call it, right, was what was interesting to Hero. Because now I can easily construct, I'm going to call this point here B prime. Now the shortest distance between A and B prime is, of course, a straight line. So I can now construct that straight line, and this will be the point on the mirror where the light reflects from. Now I'm going to just erase the other colored lines here to get them out of the way, and point out the interesting observation about this, or the interesting consequence of this. If I draw a normal to the surface of the mirror at the point where it reflects, so this is a normal line. I guess I should have drawn this just a little bit better. I'll just fix that region up right there. If I draw a normal from this reflective surface that's perpendicular to the surface of the mirror, which I've totally destroyed here. There we go. The angle here is the same as the angle here. So we'll call this theta I and theta R. And so this normal bisects this point, which means that we now have something we can call the law of reflection, which says that the angle of incidence with respect to the normal is equal to the angle of reflection with respect to the normal. Now, of course, this also means that this angle here and this angle here are the same. That's just a consequence of geometry. But usually the way that we do it is in terms of the normal to the surface, where the normal, of course, makes a right angle with the flat mirror. And so that's the law of reflection. And Hero thought that it was a consequence of what he called the principle of least distance, right? That light is going to travel the shortest possible path that it can to get from point A to point B. As we showed earlier, any other path that we considered reflecting from the surface with rays, which are just straight lines, would be longer than this path here. And so whenever the angle of incidence is equal to the angle of reflection, we find that that is where light will reflect. We'll come to learn later that this is really not least distance, it will turn out that it's least time, because light, we'll find, will travel at the night speed, and so we can think of the distance traveled as the time it took to travel it. We can think of those two things synonymously. But when we consider transmitting through optical materials like glass, we'll discover the law of refraction, and we'll be forced to abandon least distance and embrace least time. And if you take your studies further and you get into much deeper physics, then we'll learn this is really just the principle of least action. But that's way beyond what we can talk about here. Okay, so law of reflection. The angle of incidence equals the angle of reflection.